Hello and welcome to the second linear algebra clinic. In today's clinic, we're going to go over problem set 2, which involves types of matrices. So starting off, we're told that a diagonal matrix is an n by n matrix. I'm sorry. We're given an n by n matrix A, and we're told it's diagonal. Consists of the elements with the same subscripts, right? So i.e. the 1, 1 entry, the 2, 2 entry, 3, 3 entry, so on and so forth. The trace is the sum of the diagonal elements, okay? So for the first problem, we're given 3 matrices, A, B, and C, and we are asked to determine both the diagonal and trace. So the diagonal, right, is the set 1, -5, and 9. Right, it's just these elements right here. Right, they're said to form the main diagonal. Right, and the trace of A is the sum of those, right? So it's 1 plus -5 plus 9. Right, so 1 plus -5 is -4. -4 plus 9 is 5. Right, so the trace of A is 5. And so letter B, matrix B, the diagonal is the set of elements 2, -7, and 2. And its trace is their sum, so 2 plus -7 plus 2, which is -3. Right? C. C is not a square matrix. That means there is no diagonal nor trace, right? So diagonal trace only exists for square matrices. All right, now we're given another definition. All right, square matrix is said to be nilpotent if A to the P equals the 0 matrix for some positive integer P. And if P is the least positive integer that satisfies that condition, then it's nilpotent of index P. We're asked here to show that the given matrix A is nilpotent, which I spelled incorrectly. Let's fix that. Of index 3. Okay. Right. Right. In other words, what we want to do is we want to show that A squared is not the 0 matrix and A cubed is. Is this? What's going on? Okay. Well, A squared, right, just like with real numbers, it's just
Professor, it looks like you're still working on the screen share, but I don't see you or hear you. I don't know if it's just me.
I'm back. I dropped on my main computer. The call dropped.
Got it.
Again, and it's hopefully still recording. It is. Excellent. Okay. So 1 plus 2, where was I? Right. That. All right. That right then plus -1 times 3, right? So -3, right? I'm gonna go off my notes here. 5 plus 4 minus 6. -2 minus 2 plus 3. Then 3 plus 6 minus 9, 15 plus 12 minus 18, and then -6 minus 6 plus 9. Okay, what do we get? We get, for the first row, right? 0, 3, -1, 0, 3, -1, and then 0, 9, -3. A cubed would just be A times A squared. Right, so we're going to do first row of A, first column. Well, that's nice. No work required there, right? That first row is just going to be all zeros. And in fact, since the first column of A squared is all zeros, not only is the first row going to be all zeros. Actually, I'm sorry. The first row is not all zeros. The first column, that's all zeros. Right? The first column is going to be all zeros, right? Three plus 15 minus 18, and then -1. -5 plus 6. Here we get 3 plus 6 minus 9. -1 minus 2 plus 3. 9 plus 18 minus 27. -3 minus 6 plus 9. Right, 0, 0, 0. 3 plus 15 minus 18 is 0. All right, that's 0. 3 plus 6 minus 9, 0. -1 minus 2 plus 3, 0. 9 plus 8 is 27, minus 27 is 0. Right, and then -3 minus 6, -9, plus 9 is 0. So there is the zero matrix. And since 3 is the first at which that appears, we say that A is nilpotent of index 3. And that was number 2. And so number 3 deals with inverses. And to show that A and B are inverses, so what we have to do is show that A times B gives us the 3 by 3 identity, and B times A gives us the 3 by 3 identity. All right, so let's start with A times B. Right, row 1, column 1. -11 plus 0 plus 12. Row 1, column 2. 2 plus 0 minus 2. Row 1, column 3. 2 plus 0 minus 2. All right, row 2, column 1. Negative 22 plus 4 plus 18. Row 2, column 2, 4 plus 0 minus 3. Row 2, column 3, 4 minus 1 minus 3. Row 3, column 1, negative 44 minus 4 plus 48, right? Row 3, column 2, 8 plus 0 minus 8. And then finally, row 3, column 3, 8 plus 1 minus 8. Negative 11 plus 12 is 1. 2 minus 2 is 0. 2 minus 2 is 0. Negative 4 plus 18 is 22. Minus 22 is 0. 4 minus 3 is 1. Negative 1 minus 3 is negative 4. Plus 4 is 0. Negative 44 minus 4 is negative 48. Plus 48 is 0. 8 minus 8 is 0. 8 minus 8 is 0. Plus 1 is 1. All right, that's I3. All right, that's the 3 by 3 identity. So that checks out. Now we just have to do B times A. Right, so now we do row 1 of B, column 1 of A, right? So it's row of B by column of A. Row 1, column 1, negative 11 plus 4 plus 8. Right, row 1, column 2, 0 minus 2 plus 2. And row 1, column 3, negative 22 plus 6 plus 16. Row 2, column 1, negative 4 plus 0 plus 4. Row 2, column 2, 0 plus 0 plus 1. Row 2, column 3, negative 8 plus 0 minus 8. Row 3, column 1, 6 minus 2 minus 4. Row 3, column 2, 0 plus 1 minus 1. Row 3, column 3, 12 minus 3 minus 8. All right, negative 11 plus 4 plus 8 is 1. Then we get negative 2 plus 2. Negative 2 plus 6 minus, negative 22 plus 6 plus 16, 0. Negative 4 plus 4 is 0. 1. Why did I put a minus 8 there, dear? That should have been a plus 8, right? So that was what? Row 2, column 3? Yeah, 1 times 8 plus 8. 6 minus 2 minus 4. 1 minus 1. 12 minus 3 minus 8. Which is again I3, right? So A times B is the identity. B times A is the identity. Right, so therefore A and B are inverses. All right, number 4, find the inverse if it exists. All right, so remember, not every matrix has an inverse. Until later, the process of finding the inverse of a matrix is really tedious. I'm going to need more room than that. Let's move down here. Let And so we're going to say A inverse. We're going to say it's some matrix x1, x2, x3, y1, y2, y3, z1, z2, z3. Right? And the idea is to solve for all 9 variables if possible. All right, so let's find A times A inverse, right? So what we do, row by column, right? So we're going to get x1 plus y1 plus z1. x2 plus y2 plus z2. Then x3 plus y3 plus z3. Right, now row 2, y1 plus 2z1, y2 plus 2z2, y3 plus 2z3. And then finally, row 3 by each column, x1 plus 2y1 plus 4z1, x2 plus 2y2 plus 4z2, and finally, x3 plus 2y3 plus 4z3. Let's move that over. We have to have that equal to the identity. Oops. All right, so matrix equality. Matrices are equal if and only if each corresponding entry is equal, right? So what we get is a set of 9 equations. Right. But we can kind of look at these separately, can't we? If we look. What we actually have is 3 systems of 3 equations and 3 unknowns. Right? We looked at things like this in algebra. I believe it's still taught in algebra, solving systems of equations using the method of elimination. Okay. So what did I do first? I think I did first equation plus the third plus -1 times the third, or I did -1. Yeah, no. First equation times -1 times the third equation, right? X1s will cancel out. We're left with y1 minus 2y1, which is -y1, minus 3z1 is equal to, I don't know why that should be a 1. It's equal to 1. And then I just kept the second equation. Now just add those two. So if negative z1 is 1, that means that z1 itself is -1. And now it's just a matter of backward substitution, right? Now let's plug it into this one up here, the second equation, right? We get y1 minus 2 is 0. It means y1 has to be 2. And let's plug both y1 and z1 back into this third equation. 4 minus 4 plus x1 is 0, right? So x1 has to be 0. Right, and then what I did was perform the exact same operations on the other two systems. Right, really the only thing that's going to change is the right-hand side of the equations, right? Because those are different values. So we get, make that arrow a little bit longer. That negative z2 is also equal to 1. So z2 is -1. Then when you do backward substitution, we get y2 is 3 and x2 is -2. Negative y3 minus 3z3, that's going to wind up being -1. And then y3 plus 2z3 is 0. We get negative z3 is equal to -1 this time. Which means z3 is going to have to be 1. And then when we do the backward substitution, y3 is -2 and x3 is 1. Since we're able to find values for all 9 unknowns, that means the inverse does exist. Right, so A inverse, 0 to -1, -2, 3, no, I'm sorry, I'm doing that wrong. These are columns. So 0 to -1 by column, -2, 3, -1, 1, -2, 1. Well, of course, this can always be verified as an inverse simply by doing A times A inverse and make sure that you do get the 3 by 3 identity. What is the fifth one asking? Find an upper triangular matrix A such that A cubed is equal to that. All right, so what we do is set A equal to some arbitrarily chosen upper triangular matrix. All right, well, to be upper triangular, right, every element below the main diagonal has to be 0. So there's the main diagonal for a 2 by 2, right? The elements below it is just this entry here, which has to be 0, and then this can be anything. So here is an arbitrary 2 by 2 upper triangular. Right, a squared, a times a. So row 1, column 1, x times x plus 0. Now by column 2, we're going to get xy plus xz. I'm sorry, times yz. Row 2, column 1, 0 plus 0, right? And then row 2, column 2, we just get z squared. A cubed, a times a squared. Right, so row 1, column 1, x cubed plus 0. Row 1, column 2. That entry is going to be 0, and then we just get z cubed. And remember, what do we want this to equal? We wanted this to equal 8, negative 57, right? And then 0.27. Well, this is going to make things a little bit easier, right? Because we have to have x cubed equal to 8 and z cubed equal to 27 right away. That means x has to be 2 and z has to be 3. Now plug those values in, right? So we're going to get 2 times 2y plus 3y plus 9y. That equals what? 10y plus 9y, so 19y. That has to equal negative 57. That means y is negative 3. So our upper triangular matrix would be 2, negative 3, 0, 3. Right, symmetric, skew symmetric. Symmetric means that A is equal to its transpose. So if a matrix is equal to its transpose, we say the matrix is symmetric. Skew symmetric. Matrix is equal to the negative of its transpose. So A transpose, remember, transpose, just flip rows and columns. So there's A transpose. Well, look at the first row of A transpose. It is the first row of A. Second row is the second row of A. Third row is the third row of A. So A transpose is equal to A. Right, so A is symmetric. B transpose, we're going to get this. So again, rows become columns. Well, if we look, right, each entry of row 1 of B transpose is the negative of the entries of row 1 and B. And it's the same thing for row 2 and row 3. That's negative B, right? So therefore we say B is skew symmetric. For C, well, notice that C is not square, right? So when you take the transpose, you're not even going to get the same dimensions, right? In fact, C is what? It is a 2 by 3. So C transpose would be 3 by 2. There's no way C can equal C transpose. And there's no way C can equal negative C transpose because they're not the same dimensions. So since C is not square, it is neither symmetric nor skew symmetric. And finally, we're given the matrix here, 4x plus 2, 2x minus 3, and x plus 1. We are told to assume that that is symmetric. We want to solve for x and then write out what the matrix B actually is. So remember, symmetric means it is equal to its transpose. So write out its transpose. Which has to equal B. This means that 4 is equal to 4. Well, that's good. X plus 2 is equal to 2x minus 3. 2x minus 3 is equal to x plus 2, and x plus 1 is equal to x plus 1, right? So that's good. Those two check out. X plus 2 equals 2x minus 3. 2x minus 3 equal x plus 2, right? Equality is symmetric. It's a symmetric relation, which means you can flip the order in which you write it. So those two are good. They say the same thing. So x plus 2 has to equal 2x minus 3. Solve for x. Subtract x, add 3. We get 5 is equal to x. Therefore, B is 4, 5 plus 2, 10 minus 3, and 5 plus 1. All right, so there's our matrix B. So in the third clinic, the next clinic, we'll look at problem set 3. Let me just stop the recording.